Okay, we're going to go over number 4 from the homework. That was a dynamite problem. And we are recording, so it's recording everything you say, Paul.
Oh, is it really?
They gave us listen up, they gave us a position function. S equals, Carly, everybody is hearing you. There's my position as a function of time. They told us that the initial velocity was 160 feet per second. That should make sense from the position function, because velocity is the derivative of position, and the derivative of that function is 160. Okay. Oh, t squared. Yep. Okay. So the first question was, how high does the rock go? So now we're going to picture the rock going up, and then what's it going to do when it's done going up?
It's going to come down.
Right. The rock's going to come up like that, and then turn around and come back down. So at this maximum height here, what's it doing at that maximum height? Stopping, because it's got to stop before it can come back down. So if the question is, how high does the rock go, we've got to figure out, when does it stop? So we're going to find the velocity. Yeah, physics. So what's my velocity function?
The velocity is...
Well, 160, right? Minus 32t, taking the derivative of that position function. That's my velocity at any given time. Yes? Yeah? Why do we seem unhappy about that?
You plug in the time and then you're going to get the answer.
Right? That's what you had before. Yeah, okay. Right? And again, when time is 0, the initial velocity was 160. That's consistent with what they told us. So I'm just going to set that equal to 0. And I'll have 160 minus 32t equals to 0. And you solve that for t. You go to the algebra and solve that. And you get what, 5? So I know that at time t equals 5, it stopped. So that's got to be where it turned around and started coming back down. That's the highest position. So now I just have to find the position at 5. So I need to find S of 5. That's going to be 160 times 5 minus 16 times 5 squared. And you plug all that good stuff in, and let's see. I came out with 400.
Ooh, I love that.
No?
No, I got that, sir. It's got 160.
Yeah, I think that's right. Okay. 160 times 5 is 800. 25 times 16 was 400. 800 minus 400 is 400. You just give me a hard time there, Paul? Probably not. Okay, good.
I said I got that.
Okay, so that was answer to part A. It went up 400 feet before it turned around. Wow. You got to be careful when they're blasting with dynamite. Boulders can go shooting up in the air and then come back down.
Yeah.
I know. What do they ask next? What's the velocity and the speed when it is 256 feet above the ground? Well, so when they're asking me, well, the velocity when the position is 256, I've got velocity as a function of time. I need to know the time when the position is 256. Yeah, so substitute. When the position is 256, I'm going to solve this equation for time.
Minus 2.
Times 2. Okay, so what do I have here? I'm going to get everything on one side. It's quadratic. 16t squared minus 160t plus 256 equals 0. You've got a greatest common factor, please. Yeah, pull out a 16. T squared minus 10t plus 16 times what is 256? 16. And then you factor t minus 2 and t minus 8. There are two times when the position is, where's my question again? Oh, 256 feet above the ground. Once on the way up and once on the way down. There's a roll of paper towel in the green cabinet. I think all the tissues are gone. So there's my two times. So now I want the velocity at those 2 times, right? So now I'm going to find velocity at time 2. Well, my velocity function was what? 160 minus 32t. And you evaluate that, and what did I get? Let's see, I got 96. You find it, Paul? Yep. Good. And you do the same thing for v of 8. Put in an 8, and hopefully you found negative 96. So it's moving at 96 feet per second in the positive direction. That's our upward direction at 2 seconds. And moving downward at 96 feet per second for a negative velocity at 8 seconds. And in both of those times, it's 256 feet above the ground. What's my speed? 96. It's the absolute value of that velocity. So speed at either time is 96 feet per second. A lot of kinetic energy. We're not going to do much with. We'll do a little extra credit thing with the kinetic energy. A little physics problem at some point.
Count me in. I love me some good extra credit.
Need that. Gotta have that. Okay. So for C, what's the acceleration? Well, if velocity was 160 minus 32t, acceleration is a derivative. Yeah, which is just negative 32. What are the units on that? Yeah. Is that the right value for gravitational acceleration? Close enough. Okay. So the only force acting on this rock is just gravity pushing it back down. Oh, it's amazing how it all works out with the calculus, right? It's a lot of gravity. Yeah, gravity accelerates things very quickly. Meters per second squared. This is feet per second squared. Okay, where are we? D. When does the rock hit the ground?
That's why I was confused.
When?
It's at
10. How do you know 10? Well, look at that. Wait, where was it? Where did it go? Here. We found, guys. Oh, wait, no, not that one. T. We never found the zeros. We want to find the zero. No, that was a velocity. So let's go through and do this. When does it hit the what? When does it hit the ground? When what? Say that again. Yeah, you want when s is equal to 0. Right, it starts at the ground, goes up, comes back down. I won't even respond to that, Will. So I'm going to take my position function and set that equal to 0, which was 160 t minus t squared. Does anybody see why it's position? Why are we not setting the velocity equal to 0? Yeah, it's moving very quickly at the moment it hits the ground, and then all these equations stop being valid once you've hit the ground, because you got all other forces acting in play. This is only when it's in that free motion going up and coming back down. So what I'm going to do is set the position equal to 0, and I can solve that, and I get, yes, 160 minus 16t squared. So that's, I'm going to factor out my 16t. 10 minus t. So what are the two values of t for which the position is 0? 0 and 10. Which is the one that corresponds to coming back down and hitting the ground? The 10. It hits the ground after 10 seconds.
You can't hit the ground in 0 seconds.
Well, no, because that's when it starts. Yes, because if you recognize that the equation they gave you for position is a parabola, then yes, it's symmetric. But I wanted to go through this just to show how the calculus supports that as well. And if you do that on the test, just be sure you explain that in words, how you did that. Okay. Are we okay with that? So when we have our chapter test, our next chapter test.
When, next week?
No, at least 2 weeks.
No,
At least 2
I'm
weeks.
going to get 100 on that.
We should be able to do something just like that. We should be able to, this wraps up everything. We should be able to find when a particle or an object is at rest by setting the velocity equal to 0. Find when it turns around, changes direction, again where the velocity is 0. We should be able to find a time by working backwards with position. We should be able to calculate velocities from the derivative of position, calculate acceleration from the derivative of velocity, all that fun stuff. Yeah.
Is it possible to run so fast you go into the past? Yeah, it's called running fast.
Only in your world, Paul.
No. I thought, no, if you run faster than the speed of light.
I don't know.
He doesn't know.
Don't know. That's beyond me.
What's that?
Well,
Nothing's impossible.
okay. You know, if you're following the laws of relativistic motion, you cannot exceed the speed of light.
Well, there's some particles that create like
Yeah, I don't know.
They're really small.
Okay, can we move onward? Okay, Paul. Let's do it. We're gonna do an easy topic. Listen up. Oh my, excuse me. We are going to now take about a week. We're going to look at some different techniques of finding a derivative. Okay, we have learned our power rule, our quotient rule, our product rule, derivative of a sum and difference. Okay, now we're going to look at all these other different methods of finding a derivative. Some of it you've seen before, which will hopefully is easy review. Some will be new. We're going to start off with one that I know you have seen before, and that is chain rule.
Wait, do we I have a question. Is this in our notes?
No.
I gotta take my notes.
There are worksheets, but no notes. There's not a lot of notes for these. You know, the notes are very short and concise, and most of it's just we're going to do examples. You have seen chain rule before, correct?
Yeah.
Ms. Brown, did you call it the blob? The blob. The blob is back.
Wait, what was the
So I'll let you write that. I'll pause this while you write that down here. Go. So the big picture of chain rule. If I'm taking the derivative of a function whose argument is some other function of x, not x, then the chain rule says I'm going to take the, so for example, I've got a function f of g of x. That derivative will be df dg times the derivative of dg dx. Basically, you're taking the derivative of the outermost function with respect to whatever that inner blob is. Okay? And then you're going to multiply by the derivative of whatever the blob was. So here's our basic example. Let's say I've got the derivative of, I want to take the derivative of 2x plus 1 to the fourth. I want that derivative. Two x plus 1 all raised to the fourth. What we have to get in the mindset of is what's the parent function, what's the outer function, and what's the inner function. So if you look at that, if there's parentheses, what's the big thing outside the parentheses? I'm raising something to the fourth power. My parent function is something being raised to the fourth power. What am I raising to the fourth power? The blob. So this part here is my g of x. So what the chain rule is telling me to do is take the derivative of that entire thing, not with respect to x, with respect to 2x plus 1. It's a blob. If it helps, you can call it a u. We'll do that when we get to integrals. We'll do u subs. Or just think of it as a blob. This is a blob raised to the fourth. What's the derivative of a blob raised to the fourth? 4 times the blob cubed. Right. So this will become 4 times my blob cubed. But now I have to multiply by the derivative of the blob. So what's the derivative of 2x plus 1? 2. So my derivative now becomes, come back here, simplifying that, 8 times 2x plus 1 cubed. Okay? I've recognized an outer function. I took the derivative of the outer function, pretending that 2x plus 1 was my x. Right? The derivative of x to the fourth, 4x cubed. But instead of x, I've got 2x plus 1. Chain rule then says, then multiply by the derivative of that blob. That's why I got that extra 2. So we've done this before, right, with last year? No? Carl, you're shaking your head no? Should we try a few more together? Yeah. Hold on. Okay. So, we'll come back to the other way of writing it another day. So let's say I've got the derivative with respect to x of 5x plus 1 squared. What do you think, Will? What am I going to do?
5x? Wow, wait, the first one?
Yeah, first one here.
So you put the 2 in front.
Okay, because I've got a derivative of something squared, so it's 2 times that.
And then just the derivative is just 5. So, right? 5x plus 1. What?
I'm taking the derivative with respect to the blob. The blob is, so what's the derivative of blob squared? 2 times the blob, which is,
Oh, it's 2. Oh, yeah. Then the derivative of the blob.
which then gives me another 5.
He actually thought like what was going on in his mind. It was like he expected you to know that you put the blob there. But he went to the next step.
Oh, he jumped ahead a step.
That's right.
Okay.
Are you allowed to multiply that out afterwards?
If you want, sure. I would. If you want to distribute, sure, whatever you want. Just simplify or expand it as needed.
So then become
Okay.
50x plus 10.
How?
You can multiply by 10 to get
Yeah. Okay. How about this one with the square root? What's my parent function? Radical. I like to rewrite my radicals with the fractional exponent. I'm gonna rewrite that as 3x plus 1 to the 1/2. Okay. It's a power rule. I've got a blob raised to the 1/2.
Okay, and then ready? Can I do this one?
Go ahead, Paul.
Okay, so the negative 1/2.
No.
No.
What's the derivative of x to the 1/2? 1/2.
1/2.
Okay. 1/2 times
3x plus 1 to the negative 1/2.
Great. Are we done?
No.
No. What am I missing?
Try that.
Good. I'm loving it.
We got him.
Blob raised to the 1/2. 1/2 times the blob to the negative 1/2. That's the power rule part. Now the chain rule part says multiply by the derivative of the blob. Derivative of 3x plus 1 is 3.
3 times 1/2. That would be 1 and 1/2.
3 halves or 3 halves. 3x plus 1 to the negative 1/2.
Dr. Sun, do you want to go to Wendy's next year?
No. I brought my own lunch, so I'm good. But thank you for all.
Oh my god. You can get a fork.
And you should not be leaving school.
Actually,
Yeah, come on, Paul. This is a closed campus.
To close, the official response is this is a closed campus.
Okay, but also.
I'm not. No, you're on the record here. I will have your mother listen to this.
See,
If
my
you
mom said I could leave for lunch. She said, Paul, as long as you don't miss a class, I'm fine with it.
I am focused. I am so focused on calculus. I am not hearing this.
One time I had this barber
You are hearing
yelling
it.
at kids coming in saying, this is a closed campus, and I accidentally chuckled out loud.
Of
She
course
shot me
you
the
did.
nastiest look.
Of course you did. Of course. Okay. What am I gonna do with this, Jane? What are your thoughts on 1 over 5x plus 2?
Flip it to 5x plus 2 to the negative 1.
Yeah, good. Write it as with an exponent.
Good job. Is that it?
No, well, I haven't even taken the derivative yet. Now I can take the derivative. He wants to be done. We haven't even started yet.
No, oh my god.
Is it 5x plus 2?
Hey.
Okay, so now let's take the derivative.
5x plus 2.
Oh, 2. Okay, Aaron. Let's do it. Power rule.
Okay.
Let's do the power rule part.
Now it's negative 1, 5x plus 2 to the negative 2. And then multiply by 5.
Great. And if you wanted to simplify, that could simplify to negative 5 over 5x plus 2 squared.
You don't simplify those math. That's what you said.
Yeah,
That's what she said.
yeah. Simplify as needed.
That's what who said. I never know.
I never know either. Oh my goodness. Okay. Yeah, they all work about the same. Do we need to do any more of these? Or do you want to start the homework problems? So your homework problems are, look on page 8. It's a lot of problems, isn't it?
Oh, what? Okay.
And we haven't done the trig one, so let's do. We're going to come back and hit the. So I'm going to pause here.